If you are searching on how to derive maximum deflection of simply supported prismatic beam under the action of uniform load applied over its entire length using moment area method, this video is for you. Solving this problem can be carried out using simple steps, which begins with number 1, constructing the deflected shape or elastic curve and the tangents on the elastic curve. Number 2, we now analyze the geometry of the elastic curve and tangents drawn on the curve and find relationships that's equivalent to the second theorem of moment area method that in return can be converted to equation that will solve the problem. Like what we have done on cantilever beams, I have given the link in the description below. Since the beam is symmetrically loaded, maximum deflection is obviously located at midspan. Let's see will be the point at the midspan. After we draw the tangents on the curve at point C, where maximum deflection is located, we have to remember that tangents line are drawn just to touch the curve at that point. Since point C is the lowest point of the curve, the tangent line at this point is a horizontal line with zero slope. Therefore, if we want maximum deflection, we need to solve for deviation of point A with respect to a tangent at C, and from the second theorem of moment area method, that is equal to the area of the bending moment diagram between A and C multiplied by a distance from the centroid of the area up to point A divided by the flexure rigidity EI. Therefore, we need to solve the area of M over EI diagram between A and C and the centroid of area from point A, x bar A. Here is the common bending moment diagram of the beam, which leads to an equivalent area shown in the figure, which formula is unusual to solve for the properties of the area under this curve, together with the centroid because it was seldom to use. We will now use an alternative way to compute where properties of the area under the curve can be easily obtained by simple formulas that are familiar to us, yet more useful to remember. This is what we call the M over EI diagram by parts. Using equivalent cantilever beam, the idea is to make a way on how the beam will act as a cantilever beam to have areas and centroid of areas under the M over EI diagram that can be easily solved by using formulas which are familiar and easy to remember. Since we need only the area between A and C, we then consider only the portion of the beam between A and C by cutting the beam at the midspan. After cutting the beam, we will select a fixed reference point in order to have equivalent cantilever beam that in return replace the area of the bending moment diagram of the beam with the same result. In this example, point C is my fixed reference line. Point A is also possible to become fixed reference line and will also yield the same result. Selecting point C as fixed reference line, the result will be a cantilever beam under the action of a uniform load applied over the entire length of the beam and a point load applied upward at the end of the beam. We can now determine the moment reactions of the fixed support by applying equations of static equilibrium, and eventually we can now construct the bending moment diagram separately. Take note that the resulting combination of the M over EI diagram of the two cantilever beams is equal to the M over EI diagram constructed before. After constructing the bending moment diagram or the M over EI diagram, we will now determine the properties, the areas and distances, since those are what we need in computing the deflection. Area 1 is a triangular area equal to 1/2 of L over 2 multiplied by WL squared divided by 4, and it is equal to WL cubed all over 16. Area 2 is an area under a second degree curve. Therefore, the formula for area is equal to 1/3 of its base multiplied by the height. The base equal to L over 2 and the height is equal to WL squared all over 8, and the answer is equal to WL cubed divided by 48. Since x bar A is needed, we need to measure the value of the distance from the centroid up to point A, x bar 1 from the centroid of area 1 up to point A, which is equal to 2/3 of L over 2, since that area is a triangular area, and it is equal to L over 3. And for x sub 2, measured from the centroid of area 2 up to point A, is equal to 3/4 of L over 2, since that is a second degree curve, and it is equal to 3L all over 8. After solving the properties, we will now substitute it to the equation. Area 1 times x sub 1 plus area 2 times x sub 2. Since area 2 is a negative area, we have to insert the negative sign. Yields to a formula of the maximum deflection located at the midspan of a prismatic beam under the action of a uniform load applied over its entire length equal to 5WL raised to 4 divided by 384 EI, where L is the total length of the beam, W is the intensity of the uniform load, E is the modulus of elasticity, and I is the moment of inertia.